Cambridge AS Computer Science, Chapter 12, Software Development. Software development is about the organizational aspects of software development. And this is rather business. It's about project management rather than programming. Okay, so let us do this simple chapter. This chapter is not very complex because you don't actually do programming here. Programming is the most difficult. So this will award you plenty of easy marks. Okay, so let us go to software development. Stages in the program development cycle. There are stages. When you want to create a new program, first you do analysis of what the problem, what kind of problem you would like to tackle. Okay, so first you do analysis of the situation. Then you do a design. Design is represented in the form of pseudocode, flowchart, structured chart, structured English. You use these tools or formats to express your design. Afterwards, you do coding. You write the program using a high-level or low-level language. Afterwards comes testing. You test the software with normal test data, abnormal test data, extreme test data to discover any hidden errors and definitely fix all errors you could discover. And the last stage is maintenance. You deliver the software to the customer, and afterwards some issues arise. You have to solve this. This is called maintenance. You have to maintain the software. Okay? And the cycle may repeat because you keep doing maintenance until one day that software becomes obsolete and you can't use it anymore. And then you start another cycle of program development. You start by the analysis stage, design stage, coding stage, testing stage, and then maintenance. Okay, so analysis. The first step in solving a problem is to investigate the issues and the current system if there is one. The problems need to be defined clearly and precisely. A requirement specification is drawn. So in the analysis stage, you do requirement specification. You specify exactly what is required. The next is planning a solution, and this is design. Sometimes there will be more than one solution. You may need to decide which one is more appropriate. The third step is to decide how to solve the problem using top-down design, stepwise refinement. Okay, so all of these are done in the design stage. So in the design stage, you could do stepwise refinement, write pseudocode, flowchart, structured charts. Okay, so once this is called the analysis stage. In the analysis stage, you do problem definition, you do requirement specification or client requirement, you do documentation related to the current system, entity relationship diagram. This is in chapter 8 in database. Data flow diagram. This is similar to flow chart. but all about data. So this is the first stage of the called the analysis stage. Okay. Next comes the design stage. In the design stage, you do an identifier table. You list all variables that you are going to use in your program. You decide the data structure. Maybe you will use one-dimensional array or two-dimensional array. Maybe you need to store data in a file. So that data is kept after the program terminates. You may draw algorithms using flowchart or pseudocode. This is the design stage. Next, the coding stage. What is coding? You write the software from the design, from the pseudocode. You write the software using Python, for example, or Visual Basic, for example. Choose a suitable high-level programming language. Translation, where some syntax error may only become apparent. You may use interpreter or a compiler. And then execution, run the program and see the output. This is in the coding stage. Okay, then do testing. Only thorough testing can ensure the program works exactly. So next you do thorough testing. Okay, once there was a question that said, what stage in the system life cycle stage where an identifier table is produced? The identifier table is produced in the design stage. Where syntax errors could occur, this is in the coding stage. Where the developer discusses the program requirement with customers, this is in the analysis stage. Where a trace table is produced, this is in the testing stage. Okay? Where is the maintenance? We will discuss maintenance later at the end of the chapter. I don't know why. Okay? Maintenance will be studied at the end of the chapter. Okay? Program development life cycle follows a defined stages of analysis, design, coding, testing, and maintenance. When maintenance is no longer results in a program fit for purpose, the cycle starts again. We have models. We have models for system life cycle. We have the waterfall model. You do the analysis stage and then you finish, you go to the design. However, maybe when you go to the design, you find that some analysis is missing and you go back to the analysis stage. And when you do the design stage, you go to the coding. But during coding, you may discover that you have to go back to the design and fix things. From the coding, you go to testing. Maybe come back or continue on. From testing, you go to maintenance. This is called the waterfall model, where you have clearly defined stages. Probably you go from one stage to the next one. However, sometimes you may go back to some earlier stages for some further work. So this is the waterfall model. The arrows going down represent the fact that the result of one stage are input into the next. Analysis goes into design. Results of design go into the coding. The arrows leading back up to an earlier stage reflect the fact that often more work is required at an earlier stage due to complete the current stage. Then you need to have benefits and drawbacks of the waterfall model. simple to understand as each stage is clearly defined. So the waterfall method has clearly defined stages: analysis, followed by design, followed by coding, and then testing, and then maintenance. Easy to manage due to the fixed stages. Each stage has a specific outcome. Stages are produced and completed one at a time. Works well for small projects where requirements are very well understood. Maybe there are other models. We have the waterfall model. We also have rapid application development model, and we also have iterative model. We have three models for software development cycle. Okay, so benefits of the waterfall model: simple to understand as stages are clearly defined, easy to manage due to the fixed stages in the model. Each stage has a specific outcome. Stages are processed and completed one at a time. Works well for smaller projects where requirements are very well understood. Drawbacks of the waterfall model: no working software is produced until late during the software. Here, after coding and testing, you may have a working model or software. Maybe there are other models where it's called iterative. You have an early working model early in the process. Not good for complex and object-oriented projects. Maybe the iterative and the rapid application development model will be better in that. Poor model for long and ongoing projects. Cannot accommodate changes in requirements. If you change the requirements are in the analysis stage. You have to redo all the work again. Maybe there are other models that are more flexible than this waterfall model. We have to study them right now. So these problems will be overcome in the next model. Cannot accommodate changing requirement, difficult to measure progress within stages, integration is only done at the end, which doesn't allow identifying potential technical or business issues early. Okay, this is the waterfall model. There is another model called iterative model, where you start with a prototype and you keep adding more functionality to that prototype. This is called iterative model rather than the waterfall model. As I said, this is business. This is business. Okay? The iterative model does not attempt to start with full specification. You don't do a complete analysis and all that specification. Why? They think this would be more flexible. An iterative life cycle model does not attempt to start with a full specification of requirement. Instead, development starts with the implementation of a small subset of program requirements. Repeated iterative reviews to identify further requirements eventually result in the complete system. So you start with a small working model and repeatedly you add more requirements to it until you complete all the requirements. Benefits of the iterative model: there is a working model of the system at a very early stage of development, which would make it easier to find functional and design flows. Finding issues at an early stage of development means corrective measures can be taken more quickly. So these are the benefits of the iterative model. Some working functionality can be developed quickly and early in the life cycle. Progress can be measured. Testing and debugging of a small subset is easier. Risks are identified and resolved during iteration. Better situated for large mission-critical projects, software is produced early, which facilitates customer involvement or evaluation and feedback. Drawbacks: only large software development project can benefit from this, as it is hard to break a small software into small parts. If your software is already small, you cannot do iterative because it is just one task. More resources may be required. Design issues might arise because not all requirements are gathered at the beginning. You better have all the requirements to do the best design. Okay, so that was iterative model. Then rapid application RAD model is a software developed methodology that use minimal planning. You have very little planning. Instead, it uses prototyping. A prototyping is a working model of part of the situation, of the solution. In the RAD model, modules are developed in parallel. So this distinguishes it from the iterative model. In the iterative model, you start with one prototype. Here, you start with several parallel prototypes, and you build them in parallel. So a module is part of a program. Modules are developed in parallel as prototypes and are integrated to make the complete product for fast product delivery. There is no detailed pre-planning. Changes are made during the development process. So it is rather strange. You start with many working prototypes and you keep adding functionality to them until you finally bind them together. Analysis, design, coding, and test are incorporated into a series of short iterative development cycle. This is called the RAD application development model. In RAD, modules are developed in parallel as prototypes. Minimal or no detailed planning is carried out. Flexible development, small incremental releases are made. Used for time-critical development. Client involved during all stage. The benefit of RAD is that you have connection, involvement of the client. Okay? Benefit: changing requirements can be accommodated, progress can be measured, productivity increase, reduce development time, increase reusability, quick initial reviews occur, encourage customer feedback, integration from the very beginning, solve a lot of integration issues. Problem: only system that can be modularized. So if a system can be divided into modules, yes, you can do the RAD. Okay, require highly skilled developer. Only highly skilled developer can use the RAD. Only suitable for systems that are component-based and scalable. As I said, modularized. Required user involvement. So the client needs to be involved during all stages. This is a drawback because he may be busy. Only suitable for project requiring short development times. Okay? Once there was a question and it said, a program is required for a shopping website. The designer considered the use of development life cycle to split the development of the website into several stages. So he is talking about the waterfall model. He is talking about the waterfall model. Benefit of using a development life cycle. What are the benefits of using the waterfall method? Number one, easier to manage and plan. Number two, clear deliverable products at the end of each stage. Okay, analysis is one stage of a development life cycle. Documents may need to be produced during the analysis stage of the website project. What are the documents that need to be produced in the analysis stage? You need to produce the problem definition. What is the problem you need to solve? Requirement specification. This is called client requirement. Documentation related to the current system, for example, ER diagram or DFD. DFD called data flow diagram. These are all done in the analysis stage. Okay, now the program will be developed using the Rapid Application Development RAD. What are the principles of this life cycle? Number one, modules are produced in parallel as prototypes. Minimal and no detailed planning is carried out to allow for change in requirement. Flexible development process, small incremental releases are made, used for time-critical development, client involvement during all stages. These are the principles of the RAD lifecycle. What are the benefits of RAD? Quicker development is possible as multiple areas can be worked on at the same time. Prototype produced at early stage. You may have a model of the software running at early stage. Easier to change requirements. Early review is possible. The customer can look at the product early in the stages. Drawbacks, difficult to estimate cost and time to complete projects. Documentation is often omitted. Lack of client availability. The client is busy and I need his involvement. This would be would make would be an issue. Also, the client may also keep changing their mind. Okay, so that was about software development lifecycle. Please go to page 306. This question from AS22 June paper 32, the question says, the following diagram shows the incomplete waterfall model of the program development life cycle. Complete the diagram. So analysis goes down to design, and design goes down to coding, and coding goes down to testing, and afterwards the last stage is maintenance. So please draw this. So see, easy marks. Explain the meaning of the downward and upward arrows. What is the meaning of the downward arrows? It means that the result from one stage will be the input to the next stage. Okay? What is the meaning of that upgoing arrow? It means that you need to go back and solve some issues in the previous stage to complete the current stage. So please, in the downward arrow, explaining result from one stage is input into the next stage. So downward arrows result from one stage is input to the next stage. Upward arrows means more work is required at a previous stage to complete the current stage. So this is the waterfall method. Identify another type of model for program development cycle. The other one is the iterative or rapid application RAD model. Okay, شباب. Let me go back and explain further topics so that we can do. This other topic is very important and it earns quite easy and good marks, called state transition diagrams. You may design a program using state transition diagram. What is meant by state? What is meant by states in the first place? For example, when you open a website, you are in a state that you haven't typed the username and password yet. But when you type it correctly, you go to another state that you are already logged in and all the website works for you. However, if you attempt entering a password 3 times incorrectly, you will go to another state called suspended or blocked. You are not even allowed to write username and passwords anymore. So software goes from one state to another like this. This is called finite state machine or state transition table. This is the table and this is the diagram. Now in the exams, they give you the table and ask you to draw the diagram. It is very, very easy to get marks. Okay? So what is finite state machine? FSM, finite state machine, is a machine that consists of fixed set of possible states with a set of inputs that change the state and a set of possible output. All what I'm saying is very critical and very important. This question nowadays comes very often in exam. So you move from one state to another. Some input will move your program from one state to another, giving some output. Okay, so this is called we draw let me go directly into it. This is the state transition table and this is the state transition diagram. Let me just explain it rather than read it because we want to understand. Let me give you the example of converting a number into its 2's complement equivalent using the FAS method. Do you remember that? That's in chapter 1, finding the 2's complement of a number, which means converting a number to its negative equivalent. Remember when I used to say, starting from the right, any zeros are copied as they are. This is the first state. Let me show you this. If you are in state 1 and you get a 0, you output a 0 and you remain in state 1. You get another 0. So this is the input and this is the output. This is very important because you will be drawing these. So if you are in state 1 and get input as 0, you output 0 and remain in state 1 until you once get a 1. Remember, the rule is starting from the right, any zeros are copied the way they are until you get the first one and it is copied the way it is. However, So when you get 1, you output 1. However, you go to another state where every 1 is converted to a 0. Every 0 is converted to a 1. And you never go back to state 1 again. Because when you get the first 1 and you output 1, you go to state 2. Is that when you input 0, you output 0 and remain in state 2. When you get 1, you output 0. When you get 0, you output 1. And you remain indefinitely in state 2. This is called a state transition diagram. This is part of the design. And it could be expressed using state transition table. And nowadays in the exam, they give you the state transition table and you need to draw the state transition diagram. Okay? So if you are in state 0, if you are in state 1 and you get a 0, you remain in state 1 and output a 0. Okay? So this is here. When you are in state 1 and input is 0, you output a 0 and you remain in state 1. However, if you are in state 1 and you get 1, you output 1 and move to state 2. If you are in state 2 and you get 0, you output 1 and remain in state 2. If you are in state 2 and you get 1, you output 0 and remain in state 2. So what is written here is totally expressed on the diagram. And this is your duty, to convert a state transition table into a state transition diagram. And you get lots of more. Let us study few examples of those state transition diagrams and state transition table. For example, for the following state transition diagram, you start in S1. And when you get low level detected, the output is activate pump and you go to S2. And if you are in S2, if you get input low level detected, you remain in S2. However, if you are in S2 and get normal level detected, you go to S3, you deactivate the pump and go to S3. However, if you go to S3, you can never get out of it. Also, in S1, if you get normal level detected, there is no output, you just go to S3. This is a state transition diagram. So the number of transitions that result in a different state, so this is a transition that result in a different state. This is a transition that results in a different state. This is a transition that results in a different state. So you have 3. The number of transition with associated outputs. This transition has an output. This transition doesn't have an output. This transition has an output. So the number of transitions with associated outputs is 2. Label X, X should be start. The final or halting state, this is S3. If you go to S3, you can never get out of it. The current state is S1, so you are in S1. And the following inputs occur. Low level, low level, low level, low level. So you are in S1. You get low level, you output activate pump, and you go to S2. And in S2, you get low level, you remain in S2. You get low level, you remain in S2. You get low level, you remain in S2. So the number of outputs is 1 because this is the only output that you will have. Activate pump. The current state will be S2 after this. Okay, that was a very easy example. Let's go to another one. A gate which is in a locked state. You have a gate. To open it, and pass through, a customer inserts a coin into a slot. That thing unlocks. When you insert a coin, it unlocks and allow the customer to push and pass through the gate. After the customer has passed through, it locks again. If a customer pushes while it is in the locked state, it will remain locked until another coin is inserted. It has two possible states, locked and unlocked. The transition from one state to another is shown in the table below. If it is locked and you insert a coin, it becomes unlocked. If it is locked and you push, it remains locked. If it is unlocked and attempt to insert a coin, it remains unlocked. It is no use to insert a coin what is unlocked. However, if it is unlocked and you pass through, it becomes locked again. The state transition diagram for this. So you start locked. You push, you remain locked. You push, you remain locked. However, you insert a coin, you become unlocked. Insert a coin again, no use. Just remain unlocked. But when you are in unlocked, you pass through, you become locked again. Okay? Very easy to draw this. Another example. A program module controls the heater. This module operates as follows. If temperature is below 10, switch the heaters on. If temperature is above 20, switch the heaters off. The following is the test data to test the system. Test data, 23 normal. Okay. The following is the state transition diagram. So you start heater off. If temperature is greater than 20, it remains off. If temperature is greater than 20, it remains off. Until once temperature is less than 10, it goes to heaters on. If it is in heaters on and temperature less than 20, it remains on. However, if it heater on and temperature greater than 20, it goes to heaters off. Okay? Another example. A greenhouse has a window that automatically opens and closes depending on the internal temperature. If temperature rises above 20, the window half opens. If the temperature rises, so you have window closed, window half open, window fully open. You have three states. Okay? So if the temperature rises above 20, the window half opens. If the temperature rises above 30, the window fully opens. If the temperature drops below 25, the window returns to half open. If the temperature drops below 15, the window fully closes. The window has three possible states: closed, half open, and fully open. The current state, if the current state is closed and temperature rises to 20, the next state will be half open. If it is half open and it is below 15, it goes to closed. If it is half open and above 30, it goes to fully open. If fully open and drops below 25, it goes to half open. This is the diagram you are expected to draw. Window closed, temperature greater than 20, you go to half. Window half, temperature below 15, you go to closed. Window half, temperature above 30, you go to fully open. You are in fully open, temperature below 25, you go to window half open. I think now you should be able to do all exercises in the classified. So we have done that. Okay. Please, you do that. This is your homework. You have the state transition diagram and you need to do the state transition table. You have to do that. This is 22 June paper 21. And previously, that topic used to be in the A2. So maybe you would like to attempt these as well. In old days before syllabus change, in 20, yeah, we did that. Insert coin. No. We didn't do that. Please, you do that. Study that. Maybe those questions are a bit complicated, but you can study them. Yeah, we have done that. You do that. No, this is A2. A bit complicated, but it doesn't matter. Okay, so you have to do up to page 322. This is what we have studied so far. Good luck for your study, inshallah. Thank you so much.